just leave it to you to do the second problem. The second problem is, we have got one discontinuity here. Now we are going to assume the following, a more general result. Assume that only finitely many discontinuities finitely many discontinuities. That is finitely many points where the function is discontinuous. Everywhere else the function is assumed to be continuous. Now show that. Let's show that. This is a very special case. Okay. So what is that you have? This is what it is. This is the situation which we have. So this is the interval AB. On AB, we assume that you have points say C1, C2, etc. Ck. There are k points where you have this continuity. Now you choose a partition. And you can choose a partition in such a way that these points of discontinuity are inside the partition. So say C, okay, you can write this Ci is Cj is contained in some Cj belongs to this somewhere. So each one is contained in some interval. Now, when you work out the UPF minus LPF, there are intervals on which the function is continuous. There are intervals on which this is discontinuous. Okay, right? Therefore, what is that you can say about the function? The function on every interval has a maximum and a minimum, and we are assuming f is a bounded function. Therefore, this is the, you can control the width of the partition in such a way that it is less than, because other places it is continuous and only here it is discontinuous. Therefore, you can control it in such a way that this particular sum will be less than epsilon for any given epsilon. What you have to do is you will have to write down the sum separately for these intervals and separately for the places where it is continuous. At the place where the function is continuous, you can choose the interval width in such a way that it is the function is the upper bound. You see what you have, mi minus mi is less than, say, epsilon divided by some b minus a or something like that. So you can choose the interval length in such a way, and then over here on these k intervals you have fi or f bounded by the max m and small m. Okay, so there you control the width. How do you control the width? control the width in such a way that the total length of this is something like a multiple of epsilon. That is possible. So you get the two upper sum, lower sum, and the difference. So they are written. So it is something like this. So in general, it is going to be a sum like this, sigma. Sum of this. So you split this sum into two parts. One for intervals which do not contain the discontinuities, and for the intervals which contain the discontinuities. And then make the total, the sum corresponding to the intervals having discontinuities small using continuity. Okay, that is by choosing the interval length small enough so that the mi minus small mi is less than by b minus a. This can be done because of the continuity of those intervals. But at these or around these points it is not possible. Okay. So there what you do? You make this small enough and make the width small enough so that the sum of the differences on these intervals, k intervals, is going to be something like less than epsilon by 2. So make the sum corresponding to the intervals on which the function is continuous plus the sum corresponding to intervals on which the function is discontinuous at a point. Because there are finitely many points, you can separate it. So no difficulty that you can choose the interval small enough so that the interval contains only one discontinuity. Now we estimate the first part separately and the second part separately so that the sum is as small as this. So I just leave that because okay. So the third problem, so we observe that the second example shows that if the function is continuous everywhere except at finitely many points, then it is going to be Riemann. I think you should put your hand on this and try to work out the estimation, because that's a good experience on how you do analysis. I just gave a hint. Now you observe the third problem that we have, that I take is this, that suppose f is from 0, 1 r, and we define, you have seen a similar one we discussed earlier, the Vishwa function. Say another version of the Vishwa function. Two complement intersection. Take the function to be equal to 0 on this interval and x on the interval q intersection. Of course, you cannot plot this function, obviously. Okay. And then, as we argued it out earlier, because you see that when you work the lower sum and the upper sum, you see that on the interval AB or interval 0, 1, you take any interval, subinterval. Excite, and so on. This contains a rational point as well as an irrational point. I think at the irrational point we have assumed the function is 0, and at the rational points we have assumed the function to be x. Okay. So you see that it has discontinuity everywhere. Now you compute the upper sum, compute the lower sum. You will see that the two are different. And then you observe that the upper integral and the lower integral are different in this case. Therefore, this is not, f is not. So we have seen a function which is not Riemann integral. In fact, we have seen the Dirichlet function, which is already not Riemann integral. The only difference is that here you set as 1 and then makes a constant. Right. So we also look at some cracks of working on this. Do the following example. This one. Take f from A to B to R on B. Negative, continuous, and assume f of c is strictly positive, c belonging to interval. So what do we have? We have a continuous function which is non-negative, and at some point it is strictly positive. Then what we want to show is integral a to b. So if you want to prove this, the first thing is that f is a non-negative continuous function on the interval AB. What does it mean? F is Riemann integral. Observe, f belongs to CAB, which implies f is Riemann integral. That means this integral exists, that is, now we want to assert that this is greater than 0. How do we work on this? Just I'm spending some time on this because usually we will have to work with this kind of problems. So we assume C is a point, and you can, without loss of time, n points you can deal almost in the same way. Now at C, f is something like this, and we are given that f is, this is Fc, and we are assuming Fc is positive. Now what does one do? It is Riemann integrable, so it is enough to compute the lower estimate and then go for the lower integral, or upper estimate and go for the upper integral. They are equal, and that's equal to the integral a to b fx dx. So we work with the lower integral. When you work with the lower integral, one thing that you observe is that since fc is positive and f is continuous and fc is positive, choose epsilon to be equal to, then there exists such that, how do you get that? So there is a delta such that on c minus delta to c plus delta, you see that FC fx minus fy is less than fc divided by 2. Okay? If so, what happens is that, see, this is fc by 2. See, the graph of the function over this interval is about this line. This is the line fc by 2. That's what it says. Easily prove this. Okay? So we have just used continuity and the fact that fc is positive. Right. Therefore, what do we do? Now let us compute the lower sum and the upper sum. So choose a partition such that c minus delta by 2 and c plus delta by 2 belong to the partition. That is, choose xi minus 1 equal to c minus delta by 2 see LPF equal to sigma then k equal to 1 to n mk where mk is minimum of, this is the lower sum. And what can you say about this lower sum? Now there would be a scenario where this is completely 0 on this side. So we do know, we'll see what we can write is this 0 is less than or equal to, and put a prime here plus points. Okay. So what I can write is the following. Now this is anyway positive, not negative. Therefore, I have 0 is less than or equal to mi, because this is positive, 0. Okay, this is less than or equal to now what can you say about this? What about mi? Mi here is the minimum value on this interval is probably fc by 2. So that is mi is greater than or equal to fc by 2. We have 0 less than or equal to into xi minus 1 is simply delta, which is less than or equal to L. Therefore, you see that LPF is bounded away from 0 by FC by 2 into delta, and FC is positive. Therefore, what does it say? LPF is positive. So LPF is so what can you do now? What else will you find? So you see that you take the what you call the least upper bound of LPF. Therefore, this implies Q belonging to partition P from all partitions. You see that this anyway exists, and you see that this is going to be greater than, this is greater than we have proved the result. Okay, so that, and this is, since f is Riemann integrable, integral a to b f dx is the same as integral a to b over integral of f dx, which is greater than or equal to by 2. So that completes the proof. So that's enough. Now a companion result of this is, which are useful in analysis, is that suppose f from AB to R is continuous, therefore Riemann integrable, and fx is greater than or equal to 0 for every x belonging to, then that is, if this is true, then f is identically equal to 0. How do we construct a proof of this? What are the conditions? F is continuous and f is greater than or equal to 0 for every x belonging to AB, and we also have integral a to b fx dx equal to 0. So our condition P is, let us examine the proof. Condition P is three things. One, f is continuous, then f is greater than or equal to 0, integral a to b equal to 0. Then condition Q is, then Q is, that is the conclusion that we are making, f is identically equal to Q. So what we are writing is P implies Q. How do you attempt the proof of this? It's quite easy. Use the previous result. I mean, you just gear it into that language. So assume, so what we you know that this is equivalent to proving not Q implies not P. This is enough. So if you prove this, this is enough. What is not Q? Not Q is the following. Not Q says that Q is f identically equal to 0. So not Q is f not identically 0. That means there exists a C belonging to AB such that f of C is positive. Okay? Apply the previous result. What does it mean? It means integral fx dx is,
hence not Q implies not P, which in turn implies P implies Q, that is f identically equal to 0.
So now let me just give some results which you can prove. I will just list them out, shown some methods of proof. In most of the cases, UPF minus LPF less than epsilon will be the strategy to prove that f is Riemann integrable. So we do some more exercises. Assume f the precondition that we assume for Riemann integrability. Then we have the following. We have, because we do not know just in this condition, you cannot say that both f and g are Riemann integrable. But what we can say is that the lower integral and the upper integral exist. So what we can say is the following: integral a to b, lower integral of that f plus g x dx is greater than or equal to integral a to b and the inequality reverses in the case of upper integral. The upper integral of f plus g is less than or equal to a to b. This is about upper integral. Make a comment about how to prove this. Although I don't want to give the details of the proof, which you can work it out yourself. It's a good exercise to learn the art of doing mathematics. Now the third condition is integral a to b alpha f this is equal to alpha integral a to b, the lower integral of, so I am talking about lower integral, and this is equal to alpha integral a to b, the upper integral of dx, alpha times the upper integral. In the first case, we have alpha positive. In the second case, alpha is. These are useful stepping stones to prove the following. That is, if f and g are Riemann integrable, f plus g is Riemann integrable, and integral of a to b f plus g dx is equal to integral f plus integral g, and so also the integral of a to b alpha f dx is equal to alpha times integral f integral a to b fx dx. Now this shows the linear space structure of the Riemann integrable functions, and this is a stepping stone to prove this. Therefore, you see that how do you proceed on this? There is a hint here. See, lower integrals are associated with LPF. So here we are working on LPF plus G, LPF, LP, G. Okay, get the right inequality and then make the argument. Similarly, when you work with the upper integral, then you are working with UP f plus g, UPF, UPG, and write down the inequality for that and make an argument. And here, of course, there are two different cases when alpha is positive and alpha is negative. The lower integral of alpha f is equal to alpha times the lower integral of f whenever alpha is positive. But the whole thing reverses when alpha is negative. because you can actually see that for the negative part, the sort of approximation changes. Okay. So I think that's a place where we can stop this lecture, and I will do some more exercises which are very crucial in further advancement of these lectures. Thank you very much.